So we are now on the 5th chapter of Mechanics 107, and this is all about stresses in beams. So from the previous chapter, we have engaged on the stresses in bars that is caused by axial loading and torsion. So sa chapter naman na to, we will be considering the third fundamental loading, which is the bending. So it is very important to understand the stresses because any design or analysis of a beam involves calculations. So for example, if we apply a load in a beam, so kunwari meron tayong rectangular beam dito. If we apply a load in a beam, it will result into bending. Tama? So kung mag-a-apply tayo dito ng loads ng beam, magkakaroon siya ng deformation or what we call the bending. So magkakaroon ng bending ang ating beam. So parang ganito yung magiging itsura ng, so this is just an exaggerated illustration ng bending ng ating beam kung maloload siya ng certain force or a certain load. So it will generate internal stresses which can be represented by what we know the shear force and then a moment. So magkakaroon ng shear force and bending moment. So these are the internal stresses. So the shear force is the resultant of the vertical shear stress that acts parallel to the cross section of the beam, and then the bending moment is the resultant of the normal stresses or what we call the bending stress that acts perpendicular to the cross section. So kindly take note that the stresses caused by the bending moment are known as the bending stress or the flexure stress. So again, the stresses caused by the bending moment is known as the bending stress or what we call the flexure stress. So on this chapter, we will be deriving the relations between the bending moment and the flexure stress, and then the vertical shear and the shearing stresses. So in deriving these relations, we are assuming or we are making some assumptions. So we have here 5 assumptions. Assumption number 1, the plane sections of the beam remain plane. So we have here a rectangular beam. So the plane sections are plane on the entire length. Assumption number 2 says that the material in the beam is homogeneous and obeys Hooke's law. So the entire length, for example, kung concrete yung ginamit, concrete lahat the entire length. So we are assuming that the material being used is homogeneous and it obeys Hooke's law. So ano nga ba ulit yung Hooke's law? So Hooke's law states that within the proportional limit, stress is directly proportional to strain. Thus, na-derive natin yung formula in which the stress is now equal to the product of the modulus of elasticity and then the strain. And assumption number 3, the moduli of elasticity for tension and compression are equal. Assumption number 4, the beam is initially straight and of constant cross section. So we will be considering that the beam is initially straight. So no deformation, no bending. So it is initially straight. And assumption number 5, the plane of loading must contain a principal axis of the beam cross section and the loads must be perpendicular to the longitudinal axis of the beam. So, ano nga ba yung assumption number 5 na yan? So, that the loads must be perpendicular to the longitudinal axis of the beam. So, for example, we have here 3 forces that is being loaded in the beam. Force 1, force 2, and force 3. So, F1, F2, and F3 lie in the plane of symmetry. So, ito yung plane of symmetry kung saan nakalay yung ating 3 forces. So, since this is a plane of symmetry, of course, rectangular plane siya. Or rectangular section. And F1, F2, and F3 is perpendicular to the axis of the beam. So, tama. Axis, the F1, F2, and F3 is perpendicular to the axis of the beam, which is the x-axis. So, this is x, y, and then we have this z-axis. So, mapapansin yung F1, F2, and F3 is perpendicular to the axis of the beam. So, next, we will also consider that the change of cross-sectional area or the dimension is negligible. So, as the assumption number 4 states that the beam is initially straight and of constant cross-section. So, any change of cross-sectional area or dimension is negligible. And then the deformations due to the vertical shear force are negligible also in the slender beams compared to deformations caused by bending. So, initially, straight yung ating beam. So, we also have its cross-section of the beam rotates as a rigid entity about a line which we'll be calling as the neutral axis. So, its cross-section of the beam rotates as a rigid entity about the line which we call the neutral axis. So, saan ba yung neutral axis ng beam na to? So, neutral axis of the beam. So, pag rectangular shapes lang, it is very easy to determine the neutral axis of the beam. So, this is just the center ng ating cross-section. So, ito yung ating neutral axis. So, kung cross-section yan, this is the width and this is the height. The neutral axis is located on the centroid of the rectangular section. So, kung ito yung centroid niya, ito naman yung magiging neutral axis niya. So, it is very easy to determine the neutral axis kung rectangular shapes or yung regular shapes lang. Because you are just determining or you will be getting first the centroid and then dun na malalocate yung neutral axis ng iyong beam. So, at this part, kung saan nag-act yung neutral axis niya, it has also a surface. So, magdodrawing tayo ng rectangular surface here, connecting on the neutral axis, and that is, we call the neutral surface. So, meron tayong dalawang klase ng surface dito sa beam. The neutral surface, kung saan nag-act yung ating neutral axis, and then yung ating axial plane of symmetry, kung saan nag-act yung ating mga forces. So, later on, i-describe ko sa inyo yung neutral surface, or i-define ko sa inyo further yung meaning ng neutral surface and then the neutral axis. So, this is now the meaning of the flexure stress. As I have said a while ago, this is the stresses caused by the bending moment, and the relation between these two is expressed by flexure formula. And by the way, we have two kinds of bending, which is the pure bending and then the ordinary bending. So, sa pure bending, for example, we have a beam here. The beam is only experiencing a couple, which is the moment and a vertical force acting at each side. So, tinatawag na pure bending. And then, for the ordinary bending, forces produces the bending. So, meaning there are external forces being applied now to the beam. So, meron ng external forces that is acting on the beam. So, this is called the ordinary bending or the external load acting. And this pure bending naman is the beam self-load. Nagkakaroon ng bending due to its self-weight or yung weight of the beam. While this one is made by external, or the beam is experiencing bending due to the external load. So, we have here a beam with two adjacent sections. The adjacent section of AB and CD, and they are separated by a distance dx. So, since there is a load P acting on the beam, magkakaroon ngayon ng deformation. So, there is a bending caused by load P. So, since nag-deform na yung ating beam, sections AB and CD rotate relatively to each other by amount of d theta. So, mapapansin nyo, yung AB and CD natin, nagkaroon na ng deformation or rotation relative to each other. So, ito na yung ating AB and CD. So, imagine nyo na lang na nag-apply kayo ng load dito, kaya nagkaroon ng bending sa ating beam. So, yung AB natin and CD natin adjacent, nagkaroon na ng relative amount of rotation. And it is defined as our d theta. But they remain straight and undistorted in accordance with our assumption 1. So, yung assumption 1 natin, that the plane sections of the beam remain plane. So, by the way, let us assume that our beam is composed of fibers. So, we have here our beam, and our beam is composed of many fibers. Yan. So, assume natin na it is composed of many fibers. So, fiber AC, so yung fiber natin at the topmost part is shortened, and fiber BD, which can be seen at the bottom part ng ating beam, is lengthened. So, kung ito yung original length ng BD natin, mapapansin nyo, nagkaroon siya ng increase in length. And also in AC, nagkaroon siya ng decrease in length. So, trying to draw a line that is parallel to AB. So, ito na yung C prime, D prime. Papansin natin that AC is being shortened by an amount of CC prime. So, nagkakaroon na ng compression. And then, yung BD natin has an additional increase of D prime D, which is now in tension. So, the plane containing fibers like EF remains unchanged. So, itong EF na to, walang pagbabago yung fiber. So, same length pa rin yung EF natin. So, yung part na to in which the plane containing fibers is what we call now the neutral surface, because the fibers located in EF remains unchanged in length and hence carry no stress. Kaya tinatawag na neutral surface. So, dito sa EF, the fibers in EF remains unchanged and there is no change in length and they carry no stress. Kaya tinatawag na neutral surface. So, let us consider a deformation, GH, that is located y distance from the neutral surface. So, di ba yung ating deformation is equal to HK? And then, kung i-consider natin itong arc na to, yung arc natin, the deformation now is equal to y of d theta. So, yung y is equal to our, or yung ating deformation is equal to y d theta. So, ito yung kinoconsider natin na arc. Tama? So, kung kukunin natin yung value ng ating HK, it is equal to y of d theta. Kaya, ito na yun. And we know that our strain is equal to the deformation all over the original line. So, the strain is equal to the deformation, which is our y d theta. And then, yung original length natin is EF. So, bakit EF? So, as I have said earlier, EF is the neutral surface kung saan walang deformation and walang stress na nangyayari at the neutral surface. So, it is the original length. So, if we denote that the radius of the curvature of the neutral surface by our rho, so from the center up to the neutral surface, let us consider it as the rho. The curved length EF now is equal to our rho d theta. Tama? So, yung EF natin, again, is equal to, so EF, so ito na yung arc na kino-consider natin. So EF is equal to rho d theta. So if I substitute at this part, so y d theta all over rho d theta. So cancelling d theta, our strain is equal to y all over d rho. And this is now our bending strain. So assuming that the material is homogeneous and obeys Hooke's law, as I have said in assumption number 3, diba yung assumption ng yung Hooke's law natin is equal to the modulus of elasticity multiplied by the strain. So substituting the strain, so we have now this equation, and this is what we call the bending stress. So yung resultant ng forces na to must be equal to the bending moment. So we can calculate moment by the integration like this one. On which, kung isasubstitute natin yung stress dito by the bending stress, magkakaroon tayo ng pwede kong ilabas yung ating modulus of elasticity and then yung ating rho, since they are just constant. Magkakaroon na tayo ng y. And this formula looks familiar. So this formula is the area moment of inertia, right? So itong formula to is the area moment of inertia. So we can say that the moment now is equal to, and the area moment of inertia, diba yung area moment of inertia natin is denoted as our I. So let us continue here. So and then considering the bending stress on which yung modulus of elasticity natin all over rho is equal to stress all over y. So kung isa-substitute ko itong formula to at this part, we have now moment is equal to stress multiplied by the moment of inertia all over y. Therefore, our stress now is equal to moment multiplied by y all over I. So ito na yung tinatawag nating flexure formula. So this is the flexure formula, and the flexure stress is equal to the bending moment multiplied by the distance from the neutral axis to the fiber all over the moment of inertia. So this is now the formula for our flexure stress, on which our flexure stress is equal to the bending moment multiplied by distance y, or the distance from the neutral axis to the certain fiber all over the moment of inertia. So yung maximum flexure moment natin can be denoted also as Mach all over I. Yung C natin is the distance from the neutral axis, so ito yung neutral axis, to the outermost fiber ng ating beam. So kung ito yung beam natin, this is the neutral axis. So yung C na sinasabi is the distance from the neutral axis to the outermost fiber of the beam. So ito yan. Ito yung C. So the maximum of flexure stress can be found at the remotest element. And then yung y na sinasabi natin are the distances. For example, if ito yung pinapahanap, so it is denoted as y. And also, the maximum flexural stress is also denoted as the quotient of the moment all over the section modulus. So yung section modulus natin, or S, is just the quotient of the moment of inertia and the C, or the distance from the neutral axis to the remotest element. So this is what we call the section modulus, and it is denoted by S. So yung S natin, it is depending on the shape of the beam. So later on, I will be giving a copy of the properties of the different shapes of the beam. So kindly take note that positive bending moment causes negative or compressive stress above the neutral axis and positive stress below the neutral axis. So take note that the positive bending moment causes negative stress, or what we call the compressive, and it is occurring above the neutral axis, and the positive tensile stress is occurring below the neutral axis. So I repeat, positive bending moment causes negative compression. So above the neutral axis is our compression, and then below the neutral axis is our tension, and this tension is caused by a positive stress. So kaya kung napapansin nyo, yung compressive natin at the previous chapters is denoted as negative, and then yung tension natin is denoted as positive. So this is again, this is now the formula for the flexure stress, and the maximum flexure stress can be found at the outermost fiber of the beam, and also the section modulus can be equated as the quotient of the moment of inertia and the distance from the neutral. So again, this is now the flexure stress, in which the flexure stress is equal to the bending moment multiplied by the distance from the neutral axis to a certain fiber all over the moment of inertia. And then the maximum flexural stress can be found at the outermost fiber, considering it as our C. And also the section modulus is denoted by S, in which it is equal to moment of inertia all over the distance from the neutral axis to the outermost fiber. And then the positive bending moment is caused by a negative compressive stress, and it is occurring above the neutral axis, and a positive tensile stress is occurring below the neutral axis. So this is now the section modulus of the standard structural shapes. So no need naman na i-memorize nyo itong mga formula for section modulus, because as long as you know the moment of inertia, pwede nyo siyang i-derive. So section modulus, right, is equal to I all over C. So let's try for the triangle. So for the rectangle, for the rectangle, so yung I nya, if you know, is equal to BH cube all over 12, diba? So de-derive natin. So BH cube all over 12, and then yung distance from the outermost fiber, yung C natin, is equal to, so ito yan, is equal to H all over 2. So H all over 2. Therefore, it is equal to, magiging BH squared all over 6. Yan. So ito na yung section modulus ng ating rectangle. So let's try for the solid circle also. So S is equal to I all over C, on which yung I nya is equal to pi d raised to 4 all over 64. So we have pi d raised to 4 all over 64, and then yung C nya, distance from the outermost fiber to the neutral axis, is equal to d all over 2, or the radius. So d all over 2. So it is now equal to pi d cube all over 32. Yan. So lumabas yung section modulus ng solid circle. So as I have said, no need to memorize the section modulus of these shapes, as long as you know the moment of inertia. So you can derive na lang. So you can try the rest of the shapes. So we have here a summary of the procedure for determining the bending stresses. For stress at a given point, first is use the method of sections to determine the bending moment. at the cross-section containing the given point. So, as I have said earlier, napaka-importante na ma-master nyo yung method of sections or yung isang procedure, which is also the area method, in getting the shear and the moment. And then next is to determine the location of the neutral axis. So for the rectangular shapes, yung neutral axis niya is just the same location as the centroid. So mas tricky lang kung yung shape ng beam niya is an irregular one. So for number 3, compute the moment of inertia of the cross-sectional area about the neutral axis. Next, determine the y-coordinate of the given point and compute the bending stress from this equation, in which the flexure stress is equal to negative moment multiplied by y all over I. So ito yung pinaka formula talaga natin, on which we will considering y positive kung above siya ng neutral axis, above neutral axis, and then yung y naman is negative if it is below the neutral axis. So dapat uniform din yung paggamit niyo dito. So at this part, yung kung y nito, it is considered as positive, and at the below the neutral axis, y negative. Kaya kung isa-solve niyo na yung flexural stress, mapapansin niyo kung gagamit kayo dito ng positive, the flexural stress here causes a negative stress, and then the stress here causes a positive stress. So for the example number 1, a beam 150 mm wide by 250 mm deep supports the load shown. Determine the maximum flexural stress. So this is our beam with a length of 3 meters, and it has a uniformly distributed load of 6 kN per meter and a 15 kN load. So this is the cross section of our beam, 150 millimeters wide and 250 millimeters deep. So we will determine the maximum flexural stress. So the first step is to determine the maximum moment of this beam. So we will draw the shear diagram para ma-determine natin yung maximum moment. So we will use the faster method, which is the area method. So do we have a vertical force here? We have, which is 14 kilonewton. Do we have an area in the load diagram? We have, so it's 14 minus 6 multiplied by 2. So it is 2 kilonewton. So do we have a concentrated load acting on this segment? We have, which is 15 kilonewton. So 2 minus 15, negative 13 kilonewton. And then do we have an area? So meron, minus 6 multiplied by 1. So we have negative 19. So ito na yung shear diagram natin. This is the shear diagram. And then the maximum moment. Do you have a moment here? Wala, so 0. And then we have an area in the shear diagram. So 1/2 of 14 plus 2, and then yung height niya is, or yung length niya is 2 meters. So we have 16 kilonewton dot meter. And then we have a moment here, wala, and then area at this part. So 16 minus 1/2 of 13 plus 19 multiplied by 1. So 0. So ito na yung ating moment diagram. So actually, no need to draw the moment diagram as long as kaya nyo yung i-direct by looking at the shear diagram alone. So masasabi natin that the maximum moment is just equal to 1/2 of 14 plus 2 multiplied by 2. So dun lalabas yung 16 kilonewton that meter. So yun na yung maximum moment niya. So the flexural stress, we have our formula, which is Mach over I. So yung moment na gagamitin natin is 16 kilonewton that meter, or 16 times 10 raised to 6 newton that millimeter. And then yung C is the distance from the outermost fiber, or distance from the neutral axis to the outermost fiber, which is 250 divided by 2. So yung outermost fiber niya is at this part, and then yung neutral axis niya is the axis of symmetry. So this is 125 millimeter. So our C is 125 millimeter. And then yung formula ng ating moment of inertia for rectangle is BH cube all over 12. So yung B is 150 millimeter, height 250 millimeter cube all over 12. So the flexural stress is equal to it is equal to 10.24 Newton per square millimeter. So millimeter cube yan, millimeter 4, and then millimeter squared. So Newton over square millimeter, or 10.24 mega pascal. So ito na yung ating maximum flexural stress. For example number 2, a cantilever beam 50 mm wide by 150 mm high and 6 meter long carries a load that varies uniformly from 0 at the free end to 1000 Newton per meter at the wall. Compute the magnitude and location of the maximum flexural stress and determine the type and magnitude of the stress in a fiber 20 mm from the top of the beam, section 2 meters from the free end. So we have a cantilever beam that is 6 meters long. So it is fixed at the other end and free end naman sa kabila, since it is cantilever, and it is a triangular load, or it has a triangular load or a uniform varying load of 1000 Newton per meter at the fixed end, and the length is 6 meters. And then the cross section of our beam is 50 millimeters wide and 150 millimeters in height. So this is the cross section of the beam. The first step is to determine the maximum moment acting on the beam. So I will use the segment method. So we have here the cutting plane A, so dedenote ko tong Y, and this is X. So we have here the moment. So the moment is equal to 1/2 of Y multiplied by X, and then 1/3 of x. And we will determine y. So yung y natin by using a ratio and proportion. So we have here yung 1,000 Newton per meter and this is 6 meters. So kunwari ito yung x and ito yung y. So 1,000 all over 6 is equal to y all over x. Therefore, y is equal to 500 all over 3 x. So, substitute natin yung y at this part. So, palitan lang natin dito into 500 all over 3x. So, magiging 500 all over 3 multiplied by 1/2 multiplied by 1/3. So, we have 250 all over 9 x cubed kilonewton dot meter. Newton dot meter. So that's Newton dot meter. So this is now the moment at any section or at any length. So substitute lang natin yung value ng x. Therefore, the maximum moment will happen on the fixed end. So substitute lang natin yung x with 9 meters or 6 meters, sorry. Therefore, the maximum moment is equal to it is equal to 6,000 Newton dot meter. So, ito na yung maximum moment. So, the maximum flexural stress is equal to Mach all over I. So, it is equal to 6,000 Newton dot meter. And then, yung C natin, since this is a rectangular section, the distance from the outermost fiber to the neutral axis is equal to 75 millimeters. So madali lang kunin yung distance from the outermost fiber if it is in a regular shape, yung mga ganito rectangle. So pinaka-common naman yung rectangle na shape ng ating beam. So, we have here 75 millimeters. So, since meron tayo dito ng millimeters, multiply natin this one into 1,000 para maging millimeter. So, multiply natin. All over yung I, yung moment of inertia ng rectangle is equal to BH cube all over 12. So, yung B natin is 50. H natin is 150 raised to 3 all over 12. Therefore, the maximum flexural stress is equal to so it is equal to 32 Newton per square millimeter or 32 megapascal. So, the magnitude of the flexural stress is 32 megapascal and it is located 6 meters from the free end. So, it is located 6 meters from the free end. For letter B, determine the type and magnitude of the stress in a fiber 20 millimeters from the top of the beam section 2 meters from the free end. So for letter B, so ito yung cross section ng ating beam. This is 50 millimeters and this is 150. So kukunin natin yung stress 20 millimeters from the top of the fiber or top of the beam. So this is 20 millimeters. So kukunin natin yung stress at this portion. Kukunin natin yung stress ng fiber dito. So ito yung ating neutral axis. And 150, this is 75. So 75 minus 20, so this is 55 millimeters. On which yung equation natin nandito is same din. My all over I. So, yung ginamit ko na dito is y because we are determining the flexural stress at a certain point, not in the outermost fiber. So, yung C natin is just the distance from the neutral axis to the outermost fiber. And then yung Y is at any point or at any distance from the neutral axis. So, we have here, so yung moment na natin is 200, kunin muna natin dito. So, let's say M is equal to yung equation natin kanina, 250 all over 9x cubed. So, kukunin natin yung moment 2 meters from the free end. So, 2 meters from the free end. So, at this portion. So, somewhere here in 2 meters. Kaya sasubstitute lang natin ito with 2 meters. So, 250 all over 9 multiplied by 2 raised to 3. So, we have So we have 222.222 Newton dot meter. So yan yung moment niya, 2 meters from the free end. So we have 222.222. So multiply lang natin ng 1,000 para maging Newton dot millimeter. And then yung distance from the neutral axis to the point na pinapahanap. So ito yung y. So it is equal to 55 millimeters. All over moment of inertia, bh cubed all over 12. So 50 multiplied by 150 raised to 3 all over 12. Therefore, the flexural stress is equal to So it is equal to 0.8691 Newton per square millimeter, or 0.8691 megapascal. So ito na yung flexural stress natin, 2 meters from the free end. For example number 3, a high-strength steel bandsaw 20 mm wide by 0.8 mm thick runs over pulleys 600 mm in diameter. What maximum flexural stress is developed? And what minimum diameter pulleys can be used without exceeding a flexural stress of 400 megapascal? So let us assume the modulus of elasticity is equal to 200 gigapascal. So, the cross-sectional area of the steel bandsaw is equal to 20 millimeters wide and 0.8 millimeter in thickness. And then, it runs over a pulley. So, let's say this is the pulley with a diameter of 600 millimeter. So, yung diameter daw ng pulley is 600 millimeter. So, yung steel bandsaw is running at this part. So, umiikot lang siya dito. And then, we will determine the maximum flexural stress that is being developed. So, how will we determine the moment ng mga ganitong klaseng shape? So, we have a formula of the modulus of elasticity all over the rho or yung radius multiplied by the moment of inertia. So, nakuha natin yung formula na to kanina when we are deriving the flexure formula, on which yung stress natin is equal to Mach all over I. So, substitute lang natin yung moment. So, we have I, then over I. So, makakancel lang at this portion. So, we have the value of the modulus of elasticity of 200 gigapascal. And then, meron din tayong value ng C, or the distance from the neutral axis to the outermost fiber. And then, we have the rho, or yung radius. So, yeah, direct substitution lang. So, we have 200 gigapascal or 200,000 Newton per square millimeter multiplied by C. So, yung C natin. So, ito yung neutral axis. So, the distance from the neutral axis to the outermost fiber is equal to 0.4 millimeter. So, 0.4 millimeter all over the radius. So, yung radius is equal to 600 all over 2, or 300 millimeter. Therefore, the maximum flexural stress that is being developed is equal to 266.667 Newton per square millimeter, or megapascal. So, ito yung sagot ng ating letter A. And then for letter B, what minimum diameter pulleys can be used without exceeding a flexural stress of 400 megapascal? So, for letter B, yung flexural stress daw natin is 400 megapascal, or this is the maximum flexural stress. So, the flexural stress is 400 megapascal. So, hahanapin natin yung minimum diameter that will not exceed a flexural stress of 400 megapascal. So, ganun din, gagamitin din natin yung equation na to, which is C all over rho. So, 400 megapascal is equal to 200,000 multiplied by C. So, 0.4 divided by rho. So, yung rho natin is equal to it is equal to 200 millimeter. But the question is asking for the diameter. Therefore, the diameter is equal to 2 multiplied by rho. So, it is equal to 400 millimeter. So, this is the minimum diameter that will not exceed a flexural stress of 400 megapascal. For problem number 4, determine the minimum height of the beam if the flexural stress is not to exceed 20 megapascal. So, this is the cross-sectional area of our beam with a width of 80 millimeters. So, hahanapin natin yung minimum height that will not exceed the flexural stress of 20 megapascal. So, the first step is to determine again the maximum moment. So, determine natin yung maximum moment by having the shear and moment diagram. So, we have here the summation of moment of R2 is equal to 0. So, R1 multiplied by 3 meters minus 5, or let's say 2.5 kilonewton per meter of 234. So, 4 meters multiplied by the moment arm of 2 meters minus 5 kilonewton. Moment arm is 2 meters. It's equal to 0. The reaction 1 would now be equal to equal to 10 kilonewton. And then having the summation of forces vertical is equal to 0. So, we have 10 kilonewton plus R2 minus 5 minus 2.5 of 4 meters is equal to 0. Therefore, the reaction at 2 is equal to 10 minus 5 minus 2. So, transpose natin. So, magiging 5 kilonewton. So, it is very important na gamay nyo na yung pagkuha ng shear and moment diagram, or yung pag-drawing ng shear and moment diagram, because the rest of your design subject, sabi ko nga, is basically magagamitan ng shear and moment diagram. So, kung hindi nyo pa masyadong gamay itong process ng shear and moment diagram, have your time to study it further. So, So, gagamitan ko na lang siya ng area method. So, we have here, we have a concentrated load at this part. So, wala. So, 0. So, do we have an area here? So, we have which is negative 2.5 multiplied of 1. So, negative 2.5 kilonewton. So, do we have a concentrated load here? We have which is 10 kilonewton, or reaction rather. Negative 2.5 plus 10, so magiging 7.5 kilonewton. So, do we have an area in the load diagram? We have which is 7.5 minus 2.5 of 1. So, we have 5. So, do we have a concentrated load? We have which is 5 kilonewton. So, 5 minus 5 is equal to 0. And then, at this part, we have an area. We have which is equal to negative 5 kilonewton. So, 2.5 times 2, so negative 5. So, yan. So, ito na yung ating magiging shear diagram. So, that's your 5. So, ito yung ating shear diagram. Next, for the moment diagram, so do we have a moment here? Wala. We have an area here. In the shear diagram, we have which is equal to 1/2 of 2.5 multiplied by 1, so 1.25, negative 1.25. And then, do we have a moment? This part, wala. And then, we have an area in the shear diagram. We have, so negative 1.25 plus 1/2 of 7.5 plus, so this one is, kalimutan ko, this one is 5 kilonewton. So 7.5 plus 5, ang height niya is 1. So we have 5 kilonewton dot meter, and then minus 1/2 of 5 multiplied by 2, so we have 0. So concave downward, and then another concave downward, so this is now the moment diagram. So, sabi ko nga, it's not necessary to draw the moment diagram anymore as long as kaya nyo nang i-manual or i-direct yung pagkuha ng moment using the area method. So, the maximum moment would now be equal to 5 kilonewton dot meter. So, pero it's better pa rin na i-drawing nyo yung moment diagram para mas ma-practice nyo pa yung paggamit ng shear and moment diagram, especially the area method. So, the maximum moment is 5 kilonewton dot meter. Therefore, the flexural stress is equal to 20 megapascal. So, our equation is Mach all over I. So, 20 is equal to yung moment natin is 5 kilonewton dot meter. So, multiplied by 10 raised to 6 para maging newton dot millimeter. And then, see, the distance from the neutral axis to the outermost fiber is h all over 2. So, h all over 2 all over yung moment of inertia is bh cube all over 12. So, yung b is 80 millimeters. Height is h, yun yung hinahanap natin, all over 12. Using your calculator, so this is h squared. So maging square root of 5 times 10 raised to 6 multiplied by so the height is equal to 136.93 millimeters. So this would be the minimum height of the beam. For example number 5, a 50 mm diameter bar is used as a simply supported beam 3 meters long. Determine the largest uniformly distributed load that can be applied over the right 2/3 of the beam if the flexural stress is limited to 50 megapascal. So we have a simply supported beam that is 3 meters long. So pag simply supported, roller sa kabila and then hinge support sa kabila, but we can disregard the horizontal force. So we have R1, R2. So what will be the largest uniformly distributed load that can be applied over the right 2/3 of the beam? So let's say i-divide natin into 3. So the uniformly distributed load is applied over the right 2/3 of the beam. So right 2/3 of the beam. So dito yan. So let us denote this as W for the uniform distributed load. This is so this is 1 meter, 1 meter, and 1 meter. So the cross section or the cross sectional area of the beam is circular in shape, and it is 50 millimeters in diameter. So this is 50 millimeters. So again, our first step is to determine the moment. Pero since unknown yung ating uniformly distributed load, expect na yung moment natin is in terms of W. So having the summation of moment at R2 is equal to 0. So we have R1 multiplied by 3 meters minus W multiplied by 2 meters multiplied by 1 meter is equal to 0. Therefore, R1 is equal to R1 is equal to, so transpose natin ito, so magiging 2/3 W kilonewton. And then taking the summation of forces vertical is equal to 0, so we have 2/3 of W plus R2 minus W multiplied by 2 is equal to 0. Therefore, R2 is equal to 2 minus 2/3. So 4/3 of W kilonewton. So we will draw now the shear and moment diagram. So do we have a load here? We have, which is 2/3 of W. So 2/3 of W kilonewton. We do not have area, so retain siya. Then we have a area in the load diagram. We have, so 2/3 minus 2. So we have negative 4/3 W. So ito na yung ating shear diagram. So, this is not in scale. Kaya kung makapansin nyo is mas maliit yung part na to. So, supposedly, mas mahaba sana yung part na to, but this is not in scale. So, by ratio and proportion, makukuha natin yung location ng ating zero shear. So, by ratio and proportion, so this is 4/3, this is 2/3. So, let's say this is X and this is 2 meters. So, we have 2/3 plus 4/3 all over 2 meters is equal to 2/3 all over X. Therefore, X is equal to 2/3. So, this is located 2/3 from point B, and then this one is, so 2 minus 2/3 is equal to 4/3. So, moment diagram, we do not have any moment here, and then we have an area from the shear diagram. So, 2/3 multiplied by 1, so 2/3, so 2/3 of W kilonewton dot meter. And then somewhere here is the maximum moment. So, 2/3 plus 1/2 of 2/3 multiplied by 4/3. So, 2/3. So, it is 8/9. So, 8/9 W of kilonewton dot meter minus 1/2 of 4/3 multiplied by 4/3. So, 0. So, ito na yung ating moment diagram, and then the maximum moment is equal to 8/9 W kilonewton dot meter. So, pwede na natin kunin yung value ng uniformly distributed load. So, we have our formula, which is equal to Mach all over I. So, yung flexural stress natin is 50 megapascal. Moment is 8/9 of W times 10 raised to 6 Newton dot millimeter. So, yung C natin, so ito yung neutral axis. So, yung C is just the radius. So, it is 25 millimeters. 25 millimeters. All over, yung moment of inertia ng circle is equal to pi all over 4 of R raised to 4. In which yung R natin is equal to 25 millimeters. Therefore, the value of the uniformly distributed load is equal to so it is equal to 0.6903 Newton per millimeter. So, gusto ko siyang i-convert into Newton per meter. So, we have 1,000 millimeter. So, it is equal to 690.2914 Newton per meter. So, ito na yung value ng ating uniformly distributed load. So, this is the largest value of the uniformly distributed load if our flexural stress is limited only to 50 megapascal. A cantilever beam, 4 meters long, is composed of two C200 by 28 channels riveted back to back. What uniformly distributed load can be carried, in addition to the weight of the beam, without exceeding a flexural stress of 120 megapascal if the webs are vertical and if the webs are horizontal? So, makaka-encounter na tayo dito ng structural elements, which is a channel of C200 by 28. So, opening your book, Strength of Materials by Andrew Peitel and Ferdinand Singer, makikita natin dito sa likod yung mga properties ng different structural sections. Like wide flange. So, meron tayong ditong wide flange. Section ng wide flange. So, makikita din dito yung shape niya. And then the different properties. Also, we have here the S-shapes or the I-beam sections. So, ano ba yung different ng I-beam section or yung S-shape compared to W-shape? Kasi parang magkaparehas lang naman sila ng picture or illustration at this part. So, just a brief discussion or brief description. Wide flange compared to I-beam section or S-shape, mas wider yung flange niya, kaya tinatawag na flange section yung W-shape. By the way, kung ito yung ating cross-section area, ito yung tinatawag na flange. Ito yung flange niya, flanges. And this would be the web. So, sa W-shape, mas wider yung flange niya compared sa ating I-shape or yung ating S-shape. So, another shapes, we have also here the channel section. So, yung gagamitin natin is C200 by 28. C200 by 28. So, makikita nyo dito. So, ito yon yung properties of channel section. C28 by 28. Ayan yung kanyang properties. So, yung designation niya, yung first numerical, yun yung depth niya. So, it illustrates the depth. And then, yung sumusunod na numerical value, dinidescribe naman niya yung theoretical mass. So, kung ito, masasabi natin na it's around 200 mm yung depth niya and yung weight niya or yung mass niya is all, let's say, 28 kilogram per meter. But, makikita natin dito sa properties niya yung exact mass, which is 27.9. Example, ito, C230 by 30. 230 yung depth niya, around 230, but not exactly 230. And then, yung kanyang theoretical mass is around 29.8. So, makikita dito yung properties. Not exactly at this part na i-describe niya yung properties, but somehow magkalapit. So, may idea na kayo on the numerical values na mabasa nyo sa mga structural properties ng light beams and columns. We also have here equal angle. So, ito, mga angles. Equal angle. We also have here, so equal angle, so meaning equal yung depth niya at this part and yung size niya at this part. We also have here an equal angle sections. So anyway, I will not give much focus on these properties of steel sections kasi you will be having a different subject for that one, which is your steel design. So may encounter nyo talaga yung different shapes, properties, and different kinds of structural shapes. So this is just a brief discussion. So here we have C200 by 28, and this is the properties as given by the problem. So we will be solving for the uniformly distributed load that can be carried in addition to the weight of the beam. So for letter A, considering that the webs are vertical. So webs are vertical. So ito yung web, tinutukoy. This is the web. The webs are vertical. So for letter A, we have the flexural stress is equal to Mach all over I. But since meron na tayong given na section na modulus, pwede natin gamitin yan. So we can say that it is M all over S. And our flexural stress is equal to 120 megapascal. And then moment. Then since it is riveted back to back, so i-consider natin twice yung ating section modulus. So 2 times S, which is 180 times 10 raised to 3 cubic millimeter. Therefore, the moment is equal to, so it is equal to 43.2 times 10 raised to 6 Newton dot millimeter, or it is equal to 43.2 kilonewton dot meter. So from the figure or from the problem, the cantilever beam is a 4 meter long. So kung ida-drawing natin, cantilever beam siya, and it is 4 meter long. So it is loaded by a uniformly distributed load, let's say W. Therefore, from this figure, we can say that the moment is equal to W multiplied by 4 meters. Then the moment arm, so yung moment na sinasabi ko is acting at this part. So, multiplied by the moment arm, which is 2. Therefore, moment is equal to 43.2 kilonewton dot meter is equal to 8W. Therefore, the uniformly distributed load is equal to 5.4 kilonewton per meter. So the uniformly distributed load is equal to 5.4 kilonewton per meter. But the problem is asking for the uniformly distributed load that can be carried in addition to the weight of the beam. So the uniform distributed load is equal to dead load plus the live load, in which yung ating uniformly distributed load can be converted into kilogram per meter, kasi yung ating dead load, by the way, is the self weight of the beam. So since hindi sinabi dito yung weight ng beam, we can assume, as I have said earlier, that the second numerical value represents the weight of the beam. So it is approximately 28 kilogram per meter. So para uniform lahat, i-convert din natin itong uniformly distributed load into kilogram per meter. Kilogram per meter by having, so 5.4, diba yung kilonewton natin is equal to kilogram meter per second squared. So meter multiplied by, so in 1 newton there is approximately 9.81 meter per second squared. Tama? So convert natin to into 1,000 pa, so times 1,000. Therefore, it is equal to 5.4 times 1,000. So it is approximately 550.46 kilogram per meter. So yan yung total na distributed load na kinikarry ng beam natin. So it is equal to 550.46 kilogram per meter, and then the dead load is a self weight, which is equal to 28 kilogram per meter, and it is back to back, so times 2 pieces plus the live load. Therefore, the live load is now equal to, this is minus 28 times 2. So it is equal to 494.46 kilogram per meter. So ito na yung additional weight na kinikarry maliban sa dead load. So, yung live load is equal to 494.46 kg per meter. And for letter B, if the webs are horizontal. So, for letter B, if the webs are horizontal, so ito yung illustration. So, from the figure or from the properties, we have the moment of inertia along y-axis, which is equal to 0.825 times 10 raised to 6. So, hindi natin basta-basta makukuha yung moment of inertia nitong figure na to. Therefore, the moment of inertia, let's say total, is equal to 0.825 times 10 raised to 6 millimeter raised to 4 plus yung ax squared natin plus ax squared. So, by the way, yung formula is equal to iy plus ax squared. So, pagkuha ng moment of inertia. So, it is equal to 0.825 times 10 raised to 6 plus yung area, this one, 3560. So, we have 3560 and then yung x, which is 14.4 squared. Therefore, it is equal to 0.825 nakalimutan kong i-multiply siya ng 2 kasi back to back siya, so multiply natin siya ng 2. So 0.825 times 10 raised to 6 plus 3560 of 14.4 squared multiplied by 2. Therefore, it is equal to, yung moment of inertia now is equal to 3126403.2 millimeter raised to 4. So, we have now our equation. Flexure stress is equal to Mach all over I. So, yung moment natin na nakuha is, yun pa rin kukunin natin. So, we have here 120. So, we have 120 megapascal is equal to the moment. And then, yung C natin is equal to yung C natin is equal to 64 as the width. So, 64 all over yung I na nakuha natin, which is 3126403.2. Therefore, the moment is equal to 120 times 3126403.2 divided by 64. Therefore, it is equal to 5862006 Newton dot millimeter, or it is equal to 5.862 kilonewton dot meter. So from this figure again, moment is equal to W multiplied by 4 meters multiplied by the moment arm, which is 2 meters. So yung moment natin is 5.862 W of 8 meters. Therefore, the W, or the uniform distributed load, is equal to 0.73275 kilonewton per meter. And then, gusto ko siyang i-convert into kilogram per meter. So, kagaya ng ginawa natin kanina, multiply natin siya ng 1,000 and then 9.81 meter per second squared. So, it is equal to 74.69 kilogram per meter. So again, the total load is equal to dead load plus live load. So 74.69 kilogram per meter is equal to yung dead load natin, which is 28 kilogram per meter. So 28 kilogram per meter plus the live load. Therefore, the live load is equal, so dead load times 2 pala kasi back to back siya, sorry. So times 2. So 74.69 minus 2 times 28. So it is equal to 18.69 kilogram per meter. So ito na yung sagot natin for letter B. So the live load is equal to 18.69 kilogram per meter.